Today we're looking at absolute value inequalities. Before we begin with the inequalities, let's review how absolute value equations can be solved. So here on this first example, the first step that we take no matter what is we want to isolate the absolute value. So here I would divide both sides by 3, and then I would have the absolute value of x minus 4 is equal to 3. So to remind you, from here it gets broken up into two different equations because there's technically two possible things that this inside could equal. So I'm going to jump down here. So the first possibility would be that x minus 4 could equal 3. But x minus 4 could also equal negative 3 because both of these have an absolute value that would equal 3. So now when we solve, we would add 4. So one answer would be x is 7, and the other answer would be x is 1. Now we haven't had to graph for our equations, but it's worth looking at here. So I'm just going to say this is 1, and somewhere down here is going to say is 7. Now because these are actual answers, they would just be like closed circles and there aren't any arrows. Okay, so this is what it would look like for the equation. Two distinct answers. Similarly, on the second example, I would begin by subtracting 6 from both sides. I get the absolute value of 2x minus 5 is equal to 13. And then I can break this up into my two equations. So the first one would be that 2x minus 5 equaled 13, and the second one would be that 2x minus 5 equals negative 13. So now when we solve, add 5, and I would get 2x equals 18, divide by 2 to get x is 9. Same thing over here, add 5, so 2x would equal negative 8, divide by 2, and x would be negative 4. So when I go to graph, I'm just going to say there's negative 4, somewhere down here is 9, and these would again just be 2 points. Now, when we introduce the inequalities, here's what's kind of interesting. Let's say on this first example that this statement right here instead said the absolute value of x minus 4 is, let's say, less than or equal to 3. So I would still have these 2 points at 1 and 7, but I want you to think about, because it's an inequality, we know we're going to have arrows in one place or another. So let's take a look at, for instance, what happens if I let x be, not 0, 2. So if I let x be 2, then up here in yellow, I would have the absolute value of 2 minus 4 is less than or equal to 3. So 2 minus 4 is negative 2. The absolute value of negative 2 is 2. Is 2 less than or equal to 3? So yeah, so that would mean that 2 would be an answer. If I kept going and I tried this for 3, it would also be that 3 would make this true. Same thing for 4, 5, 6. So the answers are going to be the two values and what's in between them. So again, that would be if it wasn't an inequality. For the equation, it is just 1 and 7. So just trying to get you think this way, or thinking where we're going here. This looks a lot like an and inequality because we've got our two endpoints, they're pointing towards each other. And then over on the second example, let's experiment with what if this statement was in fact absolute value of 2x minus 5 is greater than 13. So what happens here if I test in between negative 4 and 9, like let's say 0. So 0 is in between them somewhere. If I put 0 in for x, I'd have the absolute value of 2 times 0 minus 5 is greater than 13. So 2 times 0 is 0, 0 minus 5 is negative 5, and the absolute value of 5 greater than 13. So 5 is greater than 13. That's not true. So that means the answers are not in between them. The answers are on the outside. So you can see that something like that looks a lot like an OR. So this is where we're headed. So the two types of inequalities, or absolute value inequalities that we're going to look at here are if you have an absolute value inequality that has less than or equal to, you will always break that up into a compound inequality separated by the word and. So every time, if it's less than or equal to, it will be an and inequality. What you'll do then is you'll write two different inequalities that you'll solve. So the first inequality will be exactly as it is written, but you won't write those absolute value bars. The second inequality, you will flip the sign and you'll make the number that's on the right the opposite of what it was. So you can think of that as making it negative. Now when you go to graph, because it breaks up into an and compound inequality, the graph will look something like, sorry, I just did that backwards. Your 2 points, open or closed circles, depends on the scenario, and they'll be connected. If you have an inequality where they are greater than or equal to, those two would be separated by the word or. But just like before, the first inequality you're going to write, you keep the first one the same, just remove the bars. The second one, you again flip the symbol and make the number on the right the opposite. So these ones will look like your 2 points with the arrows pointing away from each other. Now for our examples. So I'm going to remind myself here that if I have less than or equal to, that's an and inequality. If I have greater than or equal to, that will be an or. So here on the first example, I would begin the same way we would with equations. I want the absolute value bars to be the only thing that is on the left-hand side. Once they are the only thing, I can break them up into those two ways. So just refer back to the video a little bit or just in the section of your notes right above this. The first one you're going to write, you keep everything the same, but you just don't write the bars. Okay, so everything's the same. The second one you write, you flip the symbol and make the number on the right the opposite. So I've changed the symbol to be greater than or equal to, and then I've taken the opposite of 3, which would be negative 3. And then we solve these. So here I would add 3 to both sides. I get 4x is less than or equal to 6. And then I'll divide by 4, and I get 6/4, which reduces down to 3/2. So, and if you don't like 3/2, you're welcome to use 1 1/2. So here on the second one, add 3. I get 4x is greater than or equal to 0. I'll divide by 4 and get x is greater than or equal to 0. All right, so now when I go to graph these, so let's see here, 0, say is here, and then 3/2 is 1 1/2. So when I plot these little circles here, 0 is going to have a closed circle, and then 1 1/2 is going to have a closed circle. And then the question is, should I connect these dots or should I point the arrows away? So the original problem, I have the less than. So these would be where are the answers or the absolute value is going to be less than 3. So less than corresponds to and graphs will point towards each other. For the next example, first get the absolute value to be the only thing on that side. So once I do that, I can break these apart and I'll have 3/5 x plus 4 is greater than 2. So notice everything is the same, I just don't have bars. The second one will be 3/5 x plus 4 is less than negative 2. And now we're ready to solve. So I'll have 3/5 x is greater than -2. And then here, I'm going to rewrite this. I'm going to write this as 3x over 5 because that's the same thing as 3/5 x. And that just makes it a little more obvious that I'll multiply both sides by 5. So I'll get 3x is greater than -10. And then I'll divide by 3. And one of the answers will be x is greater than -10 thirds. I'm going to leave it like that. But when I go to graph, I'll think of -10 thirds as being -3 1/3. So here on the second one, subtract 4 once again, and I'll get 3x over 5 is less than -6. Multiply both sides by 5. 3x is less than -30. Divide by 3, and x is less than -10. So when I graph, I'll have to graph -10 thirds and -10. So -10 will be somewhere down there, and then -10 thirds, like I said, if it helps you to think of this, that's -3 1/3. And these would both be open circles. So now do I need to point them towards each other or away from each other? So it started in the problem before I broke them up into 2. It was greater than, and greater than means that you have an or statement. So these will point away. For the next 2 examples, it's the same process. The only difference is I do have to do a little bit of work before I break them into 2. So on this next one, you can't break them up into 2 until you have the absolute value bars is the only thing on the left-hand side. So for this one, the first thing I would do is I do have to divide both sides by 4. So then I would have the absolute value of 2x minus 1 is less than 5. And now that I have the absolute value bars, the only thing on the left, I can break them up. So one of them is 2x minus 1 is less than 5, and then the other one is 2x minus 1 is greater than -5. So when I solve here, I'm adding 1 to both sides, and then I'm going to divide by 2 over here. Same thing, add 1 to both sides and divide by 2. Oops. I get x is greater than -2. Now when I go to decide if it's an and or an or, I'm not looking at the original, I'm looking at right before I split them up into 2. So on the first 2 examples, I was able to split them up right away. So for this one, this is where I'm looking. So here the symbol is less than. This would be an and. So I'll plot -2 and 3, open circles, but they connect to each other. So then on this next example, first I would add 8 to both sides to get 3 times the absolute value of 4x plus 5 is greater than or equal to 9. Then I'll divide by 3, get the absolute value of 4x plus 5 is greater than or equal to 3. And now I can break it apart. So one possibility would be that 4x plus 5 was greater than or equal to 3. And the second possibility would be that 4x plus 5 is less than or equal to the opposite of 3. Solving here, because I'm running out of room, I would subtract 5, and I would get 4x is greater than or equal to -2. And then I'll divide by 4, so x is greater than or equal to -2/4, which is the same thing as -1/2. And then over here, I'll have 4x is less than or equal to -8, and x is less than or equal to -2. So when I go to graph, -2 is more negative than -1/2. There'll be closed circles above each. And to determine if I need to connect them or point them away, I look at the step right before I split them up. I'm looking right here. The symbol was greater than, which means this is an OR, and the arrows will point away. For the last two, we're going to look at dealing with when we might have to flip the symbol because we multiplied or divided by a negative number. So on this example, I want the absolute value to be the only thing before I break it apart. So I got to get rid of the 7, I got to get rid of the negative 3. So I'm going to begin by getting rid of the 7. So I subtract 7 on both sides. That gives me negative 3 times the absolute value of 4x plus 7 is less than or equal to negative 9. And then I'm going to divide by negative 3. And I get the absolute value of 4x plus 7 is greater than or equal to 3. So the symbol flipped because I divided by a negative. Now that the absolute value is by itself, I'm ready to break this up into my two possible inequalities. So the first one, everything stays as is. And the second one, I flip the symbol and make the number the opposite. So in solving here, subtract 7 on both sides, I get 4x is greater than or equal to negative 4, divide by 4, and x is greater than or equal to negative 1. For the second one, same idea, subtract 7, 4x is less than or equal to negative 10, divide by 4, and I get x is less than or equal to negative 10 fourths, which is the same thing as negative 5 halves. And if it helps, you can always think of the decimal. So this is, technically negative 2.5. So when I graph, negative 2.5 or negative 5 halves is more negative than negative 1. So that would be the order. We would have closed circles. And now when I go to decide if the arrows should be pointing towards or away, again, you have to look right before you split them up. So I split them up right here. This is where I look. So the symbol here is greater than or equal to, so this is an OR, and these would point away from each other. So you have to look at this step, because if you looked at the original, you would have it, the arrows pointing towards each other. And then for the last one, same idea, subtract 14 first here. That gives me negative 2 times the absolute value of 2x plus 3 is greater than or equal to negative 30. I'll divide by negative 2, and the sign's going to flip on me again. So absolute value of 2x plus 3 is less than or equal to 15, and then I can break this up. So this would break up into 2x plus 3 is less than or equal to 15. And then 2x plus 3 is greater than or equal to the opposite of 15. So here when I subtract 3, I'll have 2x is less than or equal to 12, and x is less than or equal to 6. And down here, we would have 2x is greater than or equal to negative 18, and x would be greater than or equal to negative 9. So when I graph, I'm just sliding it over because I'm running out of room. So negative 9 on the left, 6 is on the right. Close circles above both of them. And to decide how the symbols or how the circles should be connected, I'm going to look at right before I broke them up into 2. The symbol was less than, so this is an and inequality. And these will point towards each other. When in doubt, you can always test, like pick a number that's between them or on the outside and see what happens. So like between negative 9 and 6 is 0. So I could always put 0 into the original and see if it worked out. So if I came back over here, I would have negative 2 times the absolute value of 2 times 0 plus 3 plus 14, and that should be greater than or equal to negative 16. So I'm going to write the work here kind of going backwards. So this would be negative 2 times the absolute value of 3 plus 14. So absolute value of 3 is just 3, so negative 2 times 3 is 6. Sorry, negative 6. Negative 6 plus 14 is 8. And is 8 greater than or equal to negative 16? Yes, it is. So that would mean that 0 is in the solution, and that just kind of confirms that they should be connected.